Hey guys, I am really missing you now by week 3. Here we go with our first RPJ activity. This is going to be fun. What I'm going to encourage you to do is work through this with me. This is on page 161 in your RPJ. And as I am going through it, you should just keep pausing and seeing what answers you're getting, and then you can compare yours with mine. So until we can start doing this more live, this is what we're going to do. So we are in the last activity of chapter 7, which is super exciting. We're cruising along. Side note, I was actually just thinking about this, how we have talked about this all year long. The textbooks save the easiest geometry portions for the end of the year, and wow, are we lucky that in this current situation that we find ourselves in, thankfully we are moving towards the easy stuff. Easier, quote unquote. Okay, so here we go. 7.5 is using the Pythagorean theorem. And in our essential question says, in what other ways can you use the Pythagorean theorem? So it's interesting, if you read this statement, the converse of a statement switches the hypothesis and the conclusion. I was thinking about the shoe brand Converse, and I actually just did a little bit of research and found out that the guy who created the Converse shoe company, his name was Marquise Mills. Just did some research right now. He actually developed them in 1908, which is crazy. And just kind of thinking of the meaning of the word converse, which I don't know if we've ever stopped to think about why he created this shoe company. But converse switches the hypothesis and the conclusion. So it's literally like the opposite. And so reading about this in 1908, there were no rubber shoes. He was the first guy who came up with rubber-soled shoes. So it was literally the opposite of what everyone else had come up with, which is why they became so popular. And then they were endorsed by a famous basketball player named Chuck Taylor, which is why they became known as Chuck Taylors. Anyways, getting back to this here, a converse of a statement switches the hypothesis and the conclusion. So if you have this statement, this mathematical statement that says, if P, then Q, the converse of the statement would be the opposite. If Q, then P. So imagine I said the statement, if I live in Chicago, then I live in Illinois. So the converse of that statement would say, if I live in Illinois, then I live in Chicago. And if you stop and think about that for a moment, if I live in Illinois, do I have to live in Chicago? No, I could live in Frankfurt, which is where I grew up. So sometimes the statements will be true, and sometimes, like this one, it would be false if you did the converse of that statement. So that's going to be our task in activity 1. We're going to first come up with the converse statements, and then we're going to say if they're true or false. We want to think about the true or false portion of this. It can get a little bit confusing if you split hairs on it, which I know some of you like to do. So we're going to think of these as always, sometimes, or never. So it's either always or never. Either always or never. Okay, so why don't you pause right now and try to come up with the converse of the first statement in letter A. Okay, so if A equals B, then A squared equals B squared. The converse statement would simply say, if A squared equals B squared, then A equals B. We can disprove this statement Because let's say we have a number like 4 and we square it, we would get 16. But we could also square -4 and get 16. And we all know that 4 does not equal -4. So the converse of this statement could be false, which means we're going to say this is false. So could there be a way that that would be true? Yes. It would just be the same number. Okay, moving on to letter B. If A equals B, then A to the third equals B to the third. So the converse statement would be, if A to the third equals B to the third, then A equals B. Now this statement, if we plugged in, let's go with 4 again, and we put it to the third power, we'd get 64. And if we did -4 to the third power, that wouldn't work. We would get -64. So that statement wouldn't work anyways, which means we would have to plug in 4 to the third again, which means that A does have to equal B. So this statement, the converse would be true. Okay, in letter C, if one figure is a translation of another figure, then the figures are congruent. Converse, the figures, if the figures are congruent, then one figure is a translation of another figure. Okay, if you think about this, if the figures are congruent, then one figure is a translation of another figure. That wouldn't always be true, right? So we would have to say false here, because again, we're thinking these as always or never. So always being true, never being false. We know that you can obtain a figure through other different transformations other than a translation, and they're still congruent. So it could be a reflection or a rotation. It does not have to be a translation specifically. And the last one, if two triangles are similar, then the triangles have the same angle measures. So let's start with the converse statement. If two triangles have the same angle measure, then the triangles are similar. If two triangles have the same angle measure, then the triangles are similar. Remember we talked about that crazy letters, that I had to be careful the way I said that, AAS and AAA and SSS. Those were the proofs of similarity. We know that if we know 2 of the 3 angles in a triangle, by default we know the third one because they add up to 180. So if we have 2 triangles that share the same angle measures, we know that they're going to be similar because the third angle measure has to be the same. Okay, looking at the last question there, is the converse of a true statement always true? We know that that's not true, so we're going to say no there. But is it always false? No. We can explain this by saying in the above we had some true and some false. Okay. All right, we're going to move on to activity 2. Okay, so here's where we start to connect this to the Pythagorean theorem. The converse of the Pythagorean theorem states, if the equation a squared plus b squared equals c squared is true for the side lengths of the triangle, then the triangle is a right triangle. So let's first write the converse statement, which would say, if a triangle is a right triangle, then the equation a squared plus b squared equals c squared is true for the side lengths. Okay, so we have to decide in letter A if we think the converse of the Pythagorean theorem is true or false. Okay, so I'm going to have you pause your video. Try to think about that question. Alright, so here we go. For activity A, this is true. Oh, that looks funny, but that says true. So if you think about it, if a triangle is a right triangle, okay, it's going to have two legs and it's going to have a hypotenuse. So that would mean that you could use a squared plus b squared equals c squared to find the side lengths, because we know that c is always going to be the hypotenuse. So here's where we're going to start looking at the converse of the Pythagorean theorem in action with a right triangle. So if we consider triangle DEF with sides A, B, and C, and we say that a squared plus b squared equals c squared, because we know that that's true. Remember, we proved that with the square off of side A and the square off of side B literally being equal to the square off of side C. We're also going to consider JKL triangle, where A and B are the legs, and we're going to call X the hypotenuse, and we know that K is a 90-degree angle. So what does the Pythagorean theorem tell you about triangle JKL? Now pause the video and answer these first 3 bullet points. Okay, so one thing that always happens with this lesson is people just assume that they're both right triangles and assume that Pythagorean's theorem would work. But notice that they didn't tell us that triangle DEF is a right triangle yet. So first of all, let's start with JKL. If we are going solely based off of what they gave us, and that's that K is 90 degrees and the hypotenuse is X. We know that this is hypotenuse because it's across from the right angle. The Pythagorean theorem would state that a squared plus b squared equals x squared in this case, because they're saying that the third side is x, which we know that it doesn't matter what we label it, but because they gave us an x there, we're going to say x squared. What does this tell you about c and x? Well, that would mean that c and x are the same thing. So c equals x. And then what does this tell you about triangle DEF? Well, if we know that these sides are both A and these sides are both C, then C and X, since we already know that those are equal, all 3 of the side lengths are equal, which means that in order to form that triangle, you would have to have the same 3 angle measures. So that proves that angle E is 90 degrees. Okay? Alright, if you haven't already answered that last bullet point, let's see, is that the last one, or are there 2 more? Oh, you know what? I skipped one. Let me go back for a second here. I looked at the next one. Okay, so what does this tell us about triangle DEF and triangle JKL? I think we probably already figured this out, but DEF is the same thing. It's congruent to JKL. And looking at that bullet point, that's the one that I answered on accident. We know that angle E is 90 degrees. So therefore, we can conclude that triangle DEF is a right triangle. Okay, you're probably thinking that I'm crazy right now because you're like, what is the point of this? This is all very obvious, but this is geometry proofs at its finest. Never making assumptions, looking back on this page, never making any assumptions based off of what you see, but solely off of the things that you can prove mathematically. Okay, so here's the good part. What is this for? Well, activity 3 is where we are developing the distance formula, which I know some of you have probably already started working on IXL. This is more of an advanced topic here, but we are going to come up with the crazy distance formula. I know, F word. Okay, so here we go with one of these crazy proofs. You know, I get so excited about these, but why don't you go ahead and pause the video and see if you can follow steps 1 through 7 and see if you can formulate the distance formula on your own, and then unpause it and we can do this together. Okay, so for step 1, choose 2 points on the same coordinate plane that do not lie in the same horizontal or vertical line. So it doesn't matter where you chose yours and where I choose mine. I'm just going to go right here, and I'm going to label that as x1, x sub 1, and y sub 1. And then I'm going to go here at 4, negative 4, and call that x sub 2, y sub 2. So those are fine because they're not in the same horizontal or vertical line. Okay, step 2, done with step 1. Draw a line segment connecting the 2 points. That's going to be the hypotenuse of a right triangle. Draw horizontal and vertical line segments from the points to form the legs of the triangle. Doesn't matter which way you go. If you go this way or the other way, meaning your triangle is upside down and your 90-degree angle is up to the right, it does not matter. Just like it doesn't matter if your triangle looks the same as mine, you should still be able to come up with this formula on your with your points. Use the x-coordinates to write an expression for the length of the horizontal leg. Okay, so the length of my horizontal leg goes from here to there. Now, we know that we can simply count the units on this coordinate grid, but in order for it to be the same every time, there's one thing that we always did, and hopefully you remember this from all of these times we found slope on the coordinate plane. It's, if you want to know the length of it, you just find the difference. So you are subtracting. And just as we talked about with slope, it really does not matter which coordinate you start with, because it's going to end up the same. With slope, it would naturally end up the same. But in order for this one to be the same as this, oops, yeah, that's right. If I always want it to be positive, here's this crazy thing with the distance formula. If you always want a number to be positive, stop and think about this for a minute. You can pause so I don't give you the answer, but there is something mathematically that you can do to always make your answer positive. Think about a concept that you learned last year in 7th grade, those of you that learned this. Did you come up with it? Hopefully you said absolute value. So I'm going to erase this one because that's not actually how it is in the formula, even though it wouldn't have mattered, but technically this is what the formula says. It's that the absolute value of x2 minus x1. And again, the reason they say absolute value, because if I look at my example here, this point here is 4, negative 4. And this point here is negative 2, negative 4. So let's say I subtracted my x variables like this, 4 minus -2, I would get 6. But if I went the other way, if I did -2 minus 4, I would have gotten -6. And if I want this to be the same as this, so that it doesn't matter which way I'm going, I have to always ensure that that's going to be a positive distance, because it doesn't make sense to call this line segment a -6. So again, that's why we said absolute value of x2 minus x1. Okay, so step 4 is done. Step 5 is going to be very similar. We are looking at the difference between our y coordinates so that we can find the distance between these 2 points, or the length of that line segment. So again, we're going to say y2 minus y1, but to ensure that we get a positive answer, we're going to call that the absolute value, for the exact same reason as this above. Okay, step 6 over here, substitute the expressions for the lengths of the legs into the Pythagorean theorem. So instead of saying a squared plus b squared equals c squared, we're going to replace the a squared with one of these 2 expressions. We'll say the absolute value of x2 minus x1. But we'd have to square it still, because we are only putting that in for the length of the leg, and the leg is a. So we're taking this expression, calling that the a. So the absolute value of x sub 2 minus x sub 1 squared plus the absolute value of y sub 2 minus y sub 1 squared equals c squared. Okay, and now solve the equation in step 6 for the hypotenuse. I'm going to do this in another color because it's getting kind of crazy. I'm going to go red. Okay, so if I want to solve for c, we all know that the opposite of, or the inverse operation of squaring is taking the square root. So I'm taking the square root of all of that, and that's leaving me with c equals the square root of x2 minus x1 squared plus, I'm running out of room, y2 minus y1 sub 1 squared. So I know you're probably wondering what happened to the absolute value bars. Well, when we squared it, now it doesn't make a difference, because let's go back up to this example right here. If I did 6 squared or -6 squared, it wouldn't matter. Either way, I'd get 36. So at this point down here, I can drop those absolute value bars and then just group them with a set of parentheses. Okay, so step 7, done. And to finish this one, oh, I forgot that last question. As you see in your book, though, the question says, what does the length, I'm going to write this up on the top. What does the length of the hypotenuse, sorry for my handwriting, this is me trying, tell you about the 2 points? Okay, so what does the length of the hypotenuse tell you about the 2 points? Going back to that picture there, the length of the hypotenuse here is going to tell you the distance between those 2 points. Because remember, we can easily find that when we're driving on the street this way and driving on the street this way. Those are easy city blocks. but this is a diagonal distance that we can't just count 1, 2, 3, 4, because that's not the same value as these 1, 2, 3, 4, and so on. Okay, so the answer to this question would be the distance between the 2 points. Okay, so once again, please pause the video and answer these last 2 questions on your own. Then you can unpause it and we can talk about it together. All right, so in what other ways can you use the Pythagorean theorem? That's to find the distance between 2 points. And number 5, what kind of real life problems do you think the converse of the Pythagorean theorem can help you solve? The easiest thing I can think of is the one that we keep talking about, is what is the shortest distance from one place to another? Because we're always in a hurry, so how do we get there the fastest? And I guess we're not really talking about time, we're talking about distance here. But I would say the shortest, I just spelled that wrong. Good thing I'm not a reading teacher. Distance from one place to another. Okay, I hope you did well on this. I know it's kind of crazy, but if you have questions on things, go back and rewatch the section, and you can always comment on the video or shoot me an email and we can work it out together. Thanks, guys.